Okay, fine.
सर
So
और
let's
कोई
start.
स्टूडेंट मुझे परसों ये नोट्स मांग रहा था, मैं सोचा मैं बोलूंगा।
नोट्स यू हैव लेक्चर्स, अब नोट्स पता नहीं, अब अपलोड दोबारा करने पड़ेंगे। मैंने सेव किए हैं, बट आई विल सी टू। पहले लेक्चर आप देखो, उसको स्टूडेंट को बोलो क्लास भी अटेंड करो। नंबर क्या है उसका? गिव मी हिज रोल नंबर, पहले मैं देखूंगा उसकी अटेंडेंस क्या है।
पता नहीं सर,
इसी
मुझे
रोल,
याद नहीं।
नहीं, रोल
जब
नंबर मुझे पता है,
सेव
उसको मैं
नहीं
नोट्स
था।
दूंगा। आई विल नॉट गिव टू एवरीवन।
ठीक है सर, मैं
एनीवे, जो स्टूडेंट अटेंड ही नहीं करेगा, आई विल नॉट अलाउ हिम। Okay, next is we'll be talking about today's signal flow graph. Signal flow graph. Okay. So in the signal flow graph, what is very important for us is normally we use Mason's rule or Mason's gain formula. Sometimes some books in literature has referred to Mason's gain formula, but normally Norman Nice, sorry, and other good books will name as Mason's rule. This what is very important is Mason's rule. Okay, in this case, we have to understand first some of the definitions before I will go through the complete. Then we'll take the definitions one by one. If you understand the definition, then implementation of the Mason's rule becomes very easier for us. So what we had earlier, we have seen that BDR, that means block diagram reduction technique, we call it. Block diagram reduction technique requires what it requires. It requires successive application
सर रोल नंबर 50 को एलो कीजिए, इसको कुछ नेटवर्क इशू था।
of successive application of what? Fundamental relationships. In order to arrive at transfer function. So what BDR requires, block diagram reduction technique, it will require successive applications of fundamental relationships in order to arrive at a transfer function. That means what is the meaning of this in simple words? Simple words means we had a block diagram. We used shifting of takeoff point, shifting of the takeoff point before a point to a point after the to after a block, before a block to after a block, or after a block to before a block. In this way, summing point we have used, and exchange of summers, all other rules we have used. So those are the fundamental relationships. We have applied those fundamental relationships, and then after applying those fundamental relationships, we have simplified the block diagram network, and finally we have arrived at the transfer function. So that was how we did it in case of the block diagram reduction technique. Okay. Now next, on the second, now what we are going to do today is, on the other hand, Mason's rule for reducing a signal flow. Mason's rule is used for reducing a signal flow graph to a single transfer function. To a single transfer function. So Mason's rule is basically used for reducing a signal flow graph to a single transfer function, okay, which requires the application of which requires the application of formula. So what we have, Mason's rule is used for reducing a signal flow. So we will now have, instead of block diagram reduction technique, we'll be having a signal flow graph. And that signal flow graph will be also required to reduce it to a single transfer function, just like the block diagram. But now what we require here, we don't have a fundamental relationships here or fundamental rules like 14 rules we had in the earlier block diagram reduction technique. We had 14 rules and we have to apply those rules. We don't need to apply those rules here, but we have to apply a formula. So that formula we will take later on. The formula was derived by whom? The formula was derived by S.J. Mason, the name of that engineer or scientist, when he related the signal flow graph to the simultaneous equations that can be written from the sorry that can be written from the graph. So this formula sorry this formula, if we're talking about this formula, it was derived by whom? It was derived by this S.J. Mason. So what he did, he related the signal flow graph, the graph we will be given, some type of graph we will be given. He related that with the simultaneous equations from the graph. So we have to write the simultaneous equation from the graph itself, and then we will arrive at the transfer function. Especially we'll be have non-touching loops. So in this case, specifically the existence of non-touching loops. We'll talk about this non-touching loops in just after some time. Non-touching loops, specifically the existence of non-touching loops increases the complexity of the formula. So when we have these type of loops, let's not go for the definition of this right now. So that will not be touching something. So when this non-touching loops will increase, then the formula becomes more and more complex. So lesser they are, formula is easier. More they are, formula becomes more complex, and it's almost impossible becomes to find the answer. This is the disadvantage of this. When the existence of non-touching loops will increase, so that will make the difficult formula for us. calculations will be very cumbersome, and once the calculations will be cumbersome, it will be difficult for us to arrive at the transfer function. However, many systems in nature, many systems do not have non-touching loops. So we have lots of systems where the non-touching loops do not exist. So majority of the systems are such. So this formula is suitable for those types of systems. For those systems, it's easier to use Mason's rule than block diagram reduction technique. So what we are talking about, for those systems where we do not have complexity of the non-touching loops, for those rules, it's very easy for us to use the block diagram. So Mason's rule will have several components that must be evaluated. First, we must understand the definitions. Let's understand the definitions for Mason's rule. Definitions, sorry, you can write definitions of the components of the Mason's rule. So what are those definitions? Let's see one by one. First definition is loop gain. Loop gain is first. Let me draw the diagram. Out of this, we'll see the definitions each. This is the reference for us, this diagram. I'll draw this in blue. So sorry. Just a second, we'll draw it like. Okay, this is for the sake of the definition we are writing. We are drawing this loop. Okay. So let's say this is an input R of S. This is an overall output C of S. Let's say this transfer function is G1 of S. This transfer function is G2 of S. This is G3 of S. This is G4 of S. Then this is G5 of S. Then this is G6 of S. This is G7 of S. And this is H1 of S. And this is H2 of S. This is H3 of S. Okay, so this is here, this is V1 of S. Voltage at this point is V1 of S. This is V2 of S. This is V3 of S. This is V4 of S. This is V5 of S. So this is the signal flow graph out of reference for our reference. You can have any signal flow graphs, but then for us reference is this one. Now what is a loop gain now? Loop gain, we'll move again to the black. Loop gain is product of branch gains. See, these are the gains. G1, G2, H1 is also gain. Where's the feedback gain? Where's the forward gain? That's something different. But that's a gains. So product of branch gains found how? Product of branch gains found, yeah, obtained by traversing, that's from mowing a path that starts at a node and ends at the same node. Loop banana hai. जैसे ना गोल एक loop बनाना वैसे ही. So what is that? It is basically what? It is the product of branch gains. Product branch gains can be G2, like G1. This is a branch, and for this is also a branch gain. Branch gain is this between two nodes. Any between two nodes, that's called a branch. So the product of branch gains product of branch gains found by traversing a path that starts. Traversing means mowing. That's a simple word. We can use mowing. That starts at a node. So this is a node, this is a node, this is a node where one or two, more than two branches will meet. Simple node, complex nodes, there you know that. That starts at a node and ends at the same node. And ends at the same node. Okay. Following the direction of signal flow graph, that means if you are moving in the forward direction, you have to consider this direction. That means one loop. You cannot consider here like this and then go back like this. No, that's not a loop. So you have to follow single direction of the signal flow graph. That will be considered as a direction of the signal flow graph. Direction of following the direction of signal flow. That means where the signal will be flowing in a one direction, either in the forward or in the backward. You can like this is direction. Following the direction of the signal flow without passing through any other node more than once. More than once. So that means you have to make a closed path. You have to start at a particular node, move in the direction of the arrows, that means direction of the signal flow we call it, traverse along the route, follow the direction of the signal flow, start from a node, end at the same node, follow the direction of the signal flow graph. You don't have to encounter any node more than once. Once you have to move from traverse from there, but you don't have to encounter any node more than once. If you encounter it more than once, that is a complete violation. So if you see this figure very clearly from the above figure, there are four loop gains. So I can write it here. From the above figure, there are four loop gains. There are four loop gains. So let me identify it one by one. Let's see which one will be there. Now, number one in this case will be, let me write it in the blue again. Number one in this case is this. You start from this node here, move around this path. So what are the branch gains? G2 is a branch gain and H1 is a branch gain. So first loop gain is G2 of S into H1 of S, very clearly. You start from the each and every rule of the definition it's following. You start at this node and exit at the same node. That means end at the same node. That one definition is clear. In the direction of signal flow, the flow of signal is in the forward direction here. And then without encountering any node more than once, you are encountering it once, and then you are back there. Sorry. So you have to start from the same node, exit at the same node. You are doing that. You are not encountering any node from here more than once. No, you are not encountering, but you are following the direction of signal flow. You are following that. So all the definitions, all the points are well taken by considering this node. So loop gain. So that's the first loop gain. Second loop gain we can write is, so second loop gain is, you can move here G4 into H2. See, you start at the node, exit at the same node. Finish, number one. Point number two, in the direction of signal flow graph, in the direction of signal flow graph, and without encountering any node more than once. Yeah, you are not encountering any node more than once, that's all, and you exit at the same node. So second is G2. Okay, sorry, G2 is finished first. G4, this is G4 and H2 of S. Sorry, this is G4 of S into H2 of S. Now let's see number third now. Number third is, you can see, start from this node, exit at the same node, V3, where V3 voltage is there. Start at this node, exit at the same node. Number one point is taken. In the direction of signal flow graph. Yes, in the direction of signal flow graph. Without encountering any node more than once. Yeah, this is encountered once, this is encountered once, that's all. And you are exiting at the same node. So it follows all the points which are in the definition of the loop gain. So number third will be G4. Okay, this is, sorry, this is just be G5 written here. This second, yeah, G5. This second one. Try to rub this why it's not G5. This second. It's G5 of S, and this is, I think, G6 of S. And this is G7 of S. Complete the loop. Okay. Okay, this is the arrow. Okay, so third will be G4 as S, G5 of S, and then H3 of S. That will be third. Okay, that will be third. Now let's see fourth. Fourth will be, you can see here, this is G4 and then H2. Oh, that's finished already. G4, then you can move in this direction, G6, and then you can come back to same node as H3. Sorry, I think this is H, yeah, G4, G6, and H2. I think we have written wrong. Yeah. What's this? G4, G6, and H3 should be the same. Let's, just a second. What G? Earlier, what was this? G4. Yeah, it should be. That's clear. Now, this bigger node is there. You see? G4, G6, and H2. Oh, I think we have G4, G5. We have written wrong. G4, G5, H3. That is fine. Just a second. Yeah, G4, G5, H3 is correct. Next is G4, then like this. You can see, can make try to make a loop after this. G4, G6, and H3 again. G4 of S, G6 of S, and again it will be H3 of S. H3 of S. Fine, that is fine. That will be H3 of S. G4, G6, and H3 of S. So these are all the loop gains, possible loop gains, what we will be having. So next definition is forward path gain. Is there any doubt? Any? In this case, is there any doubt?
So V can.
Kunsa?
So V1, V2, V3.
These are voltages. Leave it for the time being. We'll see it
Okay.
later on.
सर आप प्लीज जो आपने फोर्थ पॉइंट दिखाया ना इसको प्लीज आप रिपीट करेंगे एक बार
देखो एक मैं I will make an circle around this. Okay. This third is very clear. G4, okay, G5, and H3. Starting from here. Fourth, G4, I will make a dotted path. G6, okay, and again back to this point. So we are starting at the same node, starting from a node in the direction of slope signal flow graph, exiting at the same node without encountering any node more than once. So we're following all the points of the loop gain. I hope this is clear. Next. Okay. Okay, next point is the next point in this case is forward loop gain. Forward path gain, sorry. Number 2 is the forward path gain. You have to also understand what's a forward path gain. It's a product of gains found by traversing a path. That is, product of gains found by moving a path from input node. That means from we have to start from the input node to the output node. The direction will be path is very clear. Clear from where? From input node to output node, and in the direction of what? Signal flow graph, and without encountering any node more than once. That is again a fact. So it will be, definition will be the product of gains found by traversing, that's moving, traversing a path, okay, from the input node to the output node of the signal flow graph with of the signal flow graph in the direction of signal flow. That means where the signal will be moving in the direction of signal flow. Examples of forward path gain are from the above figure. See, forward path gain will be, okay, so you can have a look. It will be starting from the input node. This is input node. First of all, this is output node. So this is your input node. This is your output node. So first of all, path has to be from input to output node. Fine. So then there it has to be in the direction of signal flow. So signal flows are moving like this: input, input, input to input towards the output. So this can be one path. It is following all the points which are in the definition. That is, it's a forward path. Yeah, we are moving in the forward direction from input node to the output node. Yes. In the direction of signal flow. Yes, in the direction of signal flow without encountering any node more than once. We are not encountering any node. Uh, we are not touching any node more than once. So that's a fine definition. So then number one path will be G1, G2FS, G3FS, G4F sub, G5F, G7F. So that will be number one path. Number two path will be G1 of S, G2 of S, G3 of S, G4 of S, then G6 of S, and G7. Again, we are moving from the input node towards the output node in the forward direction, in the direction of the signal flow, without encountering any node more than once. So very clearly from this, these are the two examples. So number one forward path will be G1 of S multiplied by G2 of S multiplied by G3 of S multiplied by G4 of S multiplied by G5 of S multiplied by G7 was the last. Second will involve G6. G1 of S, G2 of S, okay, G3 of S, G4 of S, and then here we will have a G6 of S and G7 of S will remain as it is. So it is very clear this is a forward path gain. You have to remember this is a forward path gain. So next will be non-touching loops, which we have already referred, but we have not seen the definition. Non-touching loops. This is number third. Okay, non-touching loops, that do not touch, do not have any nodes in common. What are these? Loops. Sorry. That do not have any node in common. The loops that do not have any node in common are called as non-touching loops. In above figure, following are non-touching loops. Let's see the definition. What are the non that loops? There are loops. How many loops there are? But identify the loops first. 4. So let's see which of these loops are not non-touching loops, which are not touching to each other. You can see from the figure itself. Loop 1, let's say this is 1, loop 1, and loop, let's say this is 2. They are not touching each other. Loop 1, 3, and loop. All the loops with 1, they are not touching each other, but rest of the all are touching each other. That means 2, 3, and 4, which we have identified. 3 loops, they have nodes in common, but 1 have no node common with all other 3 loops. First of all, we know 4 are loops. 4 loops are in totality, there are 4 loops, but then we can also identify which of the loops are not touching each other. What does that mean? They should not have any node in common. They should not have any node in common. So we can say number 1, we can write here loop. First loop is G2 of S. What has happened? Horizon lecture gone. Just a second. What has happened? Something wrong. Just a second. It's new. Was the earlier one gone? We have deleted that, or I don't know. Second. Just a second. I don't know what we have done. Our lecture has gone somewhere. Just a second. I want to identify. This is not the one. Just seeing the. Just a second, huh? I want to see it. Cycle bin. What is that cycle? Because we have written a lot on this. What we can do, where to see the next. Problem is we have to draw this graph again. I don't know. This has gone somewhere unnoticed. Anyway, let me draw it fast. Where it has gone, and lecture has also gone. Okay. Okay, so this is the graph we have. From input node to output node, we'll be having okay. Okay, this is what we have. Then this is an input node. Input side is R of S, and this is G1 of S, S, G6 of S, and G7 of S. So this is H1 of S. This is H2 of S. This is H3 of S. Okay, then we have voltages at points V1 of S, V2 of S, V4 of S. So we are talking about the, I think we are talking about the non-touching loops. So next is, so I have told you non-touching loops are those loops which do not have any node in common. That's fine. Okay. So now in this figure, which are the non-touching loops? So loop, we had 4 G2 of S and H1 of S. Do not touch, do not touch what? G4 of S, number one, H2 of S, then comma G4 of S, G5 of S into G4 of S, G5 of S, and H3 of S. Then we had G4 of S, G6 of S, and again H3 of S. Okay. They do not touch with this, rest of all touch. So they're non-touching loops. These are, this loop does not touch with them. So these are the non-touching loops. Okay. Next is non-touching loop gains. These are non-touching loops identified. Next formula is non-touching. Next definition is non-touching loop gains. Okay. So we'll finish this. Then so it is what? It is a product of loop gains from non-touching loops taken 2, 3, 4 or more at a time. What is this? The product of loop gains from non-touching loops taken 2, 3, 4 or more at a time. So what we mean? We had non-touching loops, so we have loop gains also. So in this figure, let us see how we can see that in the above figure. ठीक है? The product of loop gains sorry, not gains, the product of loop gain, which one? That is, we know that G2 of S, H1 is isolated loop, and loop gain and a loop gain G4 of S, H2 of S. Okay, is a non-touching loop gain is a non-touching loop gain taken 2 at a time. Taken 2 at a time. So what is the meaning of this clearly? Meaning is that first of all you have to identify pair of non-touching loops. That means if the two are not touching two loops are not touching each other, then you product their loop gains. That's called non-touching loop gains, and that's called non-touching loop gains taken 2 at a time. But now you identify next So we have three combinations here. With G2 of S, you can have combination with G4 of H2 with combination of G4 of S, G5 of S, H3 of S, G4 of S, G6 of. These three combinations you can have non-touching loops taken two at a time. Now non-touching loops taken three at a time combination is not there because these three loops are touching each other. So there is no three loops which are not touching each other. So there is only one possibility. What we can say? We can say there's only one possibility of non-touching loops two non-touching loops taken two at a time. So non-touching loops taken three at a time possibility is not there because uh, other than the loop gain G2 of S, H1 of S, all the three are touching each other. So there will be no possibility. So we can say in summary, all three of non-touching loop gains taken two at a time are. So we'll see it next time. Today it's a Salah time. So we'll conclude here. Okay. I don't know why the other one has gone. I will check it. So we'll conclude here today. Recording. We'll stop the recording. Okay, Tanzi, we can send the log.